Today I want to show you a research project that I recently worked on, developed for Didymos XR in cooperation with Avisense, an AI startup that I work with. I'm going to show you the demo of the project. So what you are seeing on the left with red is the actual position and orientation of the vehicle. With blue is a simulated error of the position and orientation of the vehicle, which could represent a bad GPS signal in the real world. And with yellow is the correct position and orientation of the vehicle. Now, here is the interesting part. The corrected position and orientation is calculated by taking the wrong position of the vehicle and using onboard cameras. A computer vision network tries to predict the actual position and orientation of the vehicle. As you can see, we have two onboard cameras, one that looks in front of the vehicle and one that looks on the left of the vehicle. Let me play the video. As you can see on the right, a trail of the corrected GPS position is very close to the trail of the actual GPS position of the vehicle. Let me play it again. There, which is all over the place, and the corrected is very close to the actual. It's something that humans can do very easily. For example, if I give you a Google Maps photo of any place, and I say you are located somewhere in a radius of 50 meters, and then I give you a street view photo of your exact location. Here is on the right. You can pin me your actual location on the map very easily, because you would be like, okay, this seems to be the corner and I am close to the road, so I must be somewhere here. Humans do that very easily, and we also now have computers that can also do it. Well, now, Dimitris, you ask, why do I care about knowing my exact GPS location? And is my GPS not already good enough? Well, you don't care, but your Tesla does. You don't want it trying to go through a building or something, because the GPS tells it that it's 10 meters ahead while it's not, and it's time to take the turn. Well, of course, that's not exactly how Tesla Autopilot works, but you get the point. For autonomous agents to navigate an environment reliably, they must know their exact location. And no, your GPS is not reliable at all, especially inside the city, where buildings block the GPS signals. Unfiltered GPS signal is very noisy. Actually, here's a video of a virtual reality project that I'm working on, coming soon to the channel. As you can see, I have my girlfriend walking, holding her phone, which streams her GPS position and orientation to the server, and then Oculus consumes that position and renders an object on the top of her head. It's that object over here. If the GPS position was perfect, the object would be exactly on top of her head. But as you can see, it's not. It jumps around all over the place. And what you see, it's actually on a good day. Let's see a little bit more. Yeah, it's completely off. Okay, it goes back over her head. but it's still not very good, and sometimes it completely jumps off. Google GPS Navigator solves that problem by making a lot of assumptions. For example, where you are driving, it assumes that you must be on the road. Depending on the direction that you are heading, it guesses on which side of the road you are. It also filters the noise, taking the previous GPS positions into account, etc., etc. But still, after all that, many times it struggles and fails and shows you that you are 2 blocks off from where you are. So classic techniques are not enough. That's why networks like that were developed. So first we are going to take a high-level dive for the current literature, a very good paper that represents very well the current scientific state of where the state-of-the-art models are, or at least when I was doing research on that problem, is boosting FreeDOF. It's a very detailed paper of the solution, plus they have made their code publicly available on GitHub for anyone to see. It's also the paper that we based our solution on. It's a very good paper. I encourage you to read it yourself, as you can see, have a lot of notes. But for this high-level overview, instead of reading from the paper itself, I'm going to show you a presentation that I have prepared so you can understand better both the problem and the solution. So, before we take a dive on how the network works, we are going to take a look of the approach of how to solve the problem. So let's say that we have the exact GPS coordinates of a vehicle and its orientation from the magnetometer, and we also have the GPS coordinates of a vehicle plus some error that we model as dx, dy, dθ, where those coordinates can represent the actual GPS location that we have from our GPS, which is our true location plus some error or noise, which, if we can find, we can calculate our exact location by subtracting them. Now, for each of those, we can simply take a satellite image patch around the vehicle. So we have two image patches, one for GPS error satellite image and one for ground truth satellite image. So if we take the GPS error satellite image and translate it by dx, dy and rotate it by d theta, its pixels will fall exactly on top of the pixels of the ground truth satellite image. And then we would have found exactly our GPS error, and by default, our actual GPS location. But of course, the problem is that we don't have the ground truth satellite image because we need the ground truth GPS position, which we are trying to find. So what we do instead is we reconstruct the ground truth satellite image features from the cameras that are on top of the vehicle. On the right, we have the reconstructed ground truth satellite image from the features of the front camera. That's why you only see the front part of the image filled with features. And at the same time, we extract the features from the satellite image. And now we can compare the features of GPS error satellite image and the features of the reconstructed satellite image instead. And that way we can calculate dx, dy, dθ. So now we understand how the problem can be solved. We are going to take a look on the networks and solutions that the authors of FreeDOF use. So what the authors do first is they calculate the ground truth reconstructed satellite features and the GPS error satellite features. They subtract the one from the other and feed them to an image transformer, which tries to calculate the dx, dy, dθ. But the authors say that maybe the image transformer didn't uh, predict the dx, dy, the theta very good in the first time. So what they do is they translate the ground truth reconstructed satellite image features by dx, dy, the theta 1. And now the ground truth reconstructed satellite image features should match better the GPS error satellite image features. And they feed them again into an image transformer, which tries to calculate again the dx, dy, the theta. But this time the dx, dy, the theta should be smaller. And they add them again to dx, dy, the theta 1 and rotate and translate the ground truth reconstructed image, ground truth reconstructed satellite image features again, which should match even better the GPS error satellite image features this time, and they feed them again into an image transformer and calculate dx, dy, the theta 3. And you can do that process as many times as you like. The authors in the paper, I think they stop at 3. They see that they get the better results while keeping the computational load. So if you add all those together, you get the final predicted dx, dy, the theta. But what the authors in the paper found is that while the predicted orientation error is very good, the predicted translation dx and dy is not so good with this technique. So what they do is they just keep the theta and rotate the ground truth reconstructed satellite features. And then they take the GPS satellite features and they basically convolve the one on top of the other. And where the features match best, they say that it is the actual position of the vehicle, and that way they take the final dx, dy. So their solution, their network is basically sliced in two parts. The first part which tries to predict the rotation, and the second part which tries to predict the translation. So while the solution of the authors was pretty good, it suffers from one very big problem, like many of those networks do, which is the performance on the longitudinal direction, which I will explain to you what it is. So let's say, for example, that your actual vehicle location is right here, and your GPS says that you are over here inside the building. The network will predict with high accuracy that where you are on this axis. So basically it will predict very easily that you are on the road, but on the axis parallel to the road, this one, it has a very low accuracy, meaning that it will have a difficult time locating where exactly on the road you are, which is quite a problem. And I will show you some metrics. On the lateral direction, which is this axis, if we count the percentage, okay, excuse me, of times that the prediction of the network is within 1 meter or less of the actual location of the vehicle in the lateral direction, it will be around 77%, but only 16% for the longitudinal direction, which is this one, which is pretty bad. Azimuth for 1 degrees here means that the error of the orientation of the vehicle that the network predicts is less than 1 degree, around 54% of the time, which is totally okay. It predicts the orientation of the vehicle with high accuracy. So the intuitive approach in this case would be, okay, maybe the network doesn't have important information what is going on the left and the right of the vehicle. For example, to be able to locate in the longitudinal direction where exactly the vehicle is. For example, maybe if the network could see the stores around it. For example, let's say, okay, maybe we have one store over here, and the network could see it. It would say, okay, maybe I know exactly where I am. I am in the middle of the road here, in this direction, because I see that store, for example. But because we only have the information from the front camera, it can't look. It has very hard time locating exactly where we are on the longitudinal direction. So the simple solution would be to add one more camera, which we did. We also gave the information of the left camera to the network. As you can see, now the reconstructed GPS, but the reconstructed top-down view that the network generates also has the left features over here that are lifted to 3D. And we tested again, but we didn't see actually any improvement. The improvement here in the longitudinal direction is only 0.6%, which is not very good, which could be also by luck, depending on how long you turn the network and where you stop. So, if you think a little bit more what the authors do in their paper, you would realize that there is actually a very big problem. They use homography to reconstruct the top-down view, which is actually homography is an assumption that the world is flat. So basically, you are not lifting any features from the yes, so basically you are only lifting the features that are on the ground, and you are missing very important information, like for example, you can see the sign over here. Those features are never lifted to the top-down view. So of course the network would not be able to use that information. For example, it's the same like saying you are looking down on the ground and trying to predict where you are. You can only predict, okay, I am on the road, but exactly on which I see because I'm looking down, but exactly where on the road I am, it would be very difficult, basically impossible. You would have to look around you and lift your head. And this explains perfectly why we're seeing such a low performance on the longitudinal direction. I have to mention that in their paper, the authors say that they are using cross-attention and not just homography. Give me a second to reload. Yes, around here. They start with homography and they do cross-attention to pull again the features from the original image. But if you actually look at the code, they apply cross-attention runtime to the low-level features, which I think it's not enough to pull all that semantic information. It's not powerful enough doing cross-attention runtime on the low-level features. So it's basically the same, just as using plain homography. It's not enough doing cross attention one time. That's what we thought that was the problem. So what we did, we used a different technique. Yes, as you can see, I highlight that you are missing all those important features here, like the signs, the buildings, which are very important to locate where you are in the longitudinal direction. You're just looking down on the road. So what we did is actually discarded the homography. We did 3D lifting, which is we basically lifted the 3D volume around the vehicle and not just one slice, which was the ground. And the technique that we used, it was the same that the authors in the Simple Bev use. This is actually a very good paper. I recommend you to read it if you are interested in 3D object detection in autonomous vehicle. It's actually a very good paper. And it is a technique that is has very good performance and it is very fast. Cross attention is, while it works, it is very compute and memory heavy. That's why we use this technique. You basically take, like in homography, you only take one slice of the world, which it is the ground. In 3D lifting, we took 8 slices. So as you can see here on the left are the features, how the features look on the homography and the versus 3D lifting. You basically have the z-axis. And then you feed those 3D lifted features to a ResNet and get again homography-like shape, but this time you have all the information. And after that, we actually got 10 points of improvement. Yeah, from 11. Oh, very nice. From 15.8, we went to 26.8, and we got 83% in the rotation error, which is very good. It means the network predicts perfectly the orientation of the vehicle. And these metrics are actually on a very difficult test set. It was on a test set, not training. The log run of the Ford AV is actually just desert. It doesn't have any buildings, which would help a lot the network to find the actual location of the vehicle. So 26.8 is actually a very good number. And yeah, I will show you again around last time the demo, like I did in the beginning. As you can see, the network does pretty well. It would also be worth it to try it with more than 2 cameras, with 6 cameras, for example, looking in all directions. So yeah. So if you have any questions, feel free to make a comment. And if you want any consultation on your ML projects, I will leave a link. Thank you and bye bye.